Let's get it started.
Hi, I am Rashmi. I will be giving a brief introduction.
Hi, I am Alfred. I will discuss the algorithm.
I will be implementing the insertion in a binary search tree using a program.
Hello guys, this is Rashmi. Let's learn about insertion of a node into a binary search tree. The binary search tree, also known as an ordered binary tree, it is a node-based data structure in which each node has no more than 2 child nodes. The left subtree contains only nodes with keys less than the parent node, and the right subtree contains only nodes with keys greater than the parent node. Here 15, this is called as the parent node, or else it is also called as the root. 10 and 20 are called the child nodes of this root, and 8, 12, 17, 25 are called the leaf nodes, as they are not connected to any other further nodes. Let's see an example of how to insert a data into a binary search tree. Here 15 is the first data, or else it is also called as the root, and when 10 has to be inserted, the value is checked with the root node, whether it is greater than or lesser than the node. Here 10 is lesser than the 15, so it is inserted on left hand side of it. That means this pointer contains the address of this node, and 20 is greater than 15, so it is kept on the right hand side of it. Likewise 8, 12, 17 and 25. All these leaf nodes pointers are not yet connected to any other nodes, so they are null. The advantage of binary search tree is it remains ordered, which provides quicker search times, and it is very efficient. They are also easy to code.
A tree where each node has a left and right node. For a binary search tree, the values of the nodes that are to the left side of the root node will be lesser than the value of the root node, and the values of the nodes which are to the right side of the root node will be greater than the value of the root node. So now let's consider an integer binary search tree. Now let's talk about the insertion of a node in a binary search tree. Just assume that we have to insert an element 5 in this binary search tree. So it's work in this way. We'll compare the value of the 5 with the root node 18. So we know that 5 is less than 18, so we'll traverse the left. Basically to the left side of the root node, the values lesser than the root node are assigned, so we'll travel left side. So now we'll reach the node 15. Now we will compare the value of 5 with 15. We know 5 is lesser than 15, so we'll again travel to the left side. Now we'll compare the value of 5 with that of 10. So we know the value of 5 is less than 10, so we'll insert the node 5 here to the left side of the 10. So since 5 is lesser than 18, 15 and 10, we'll traverse to the left side to insert the node here. Basic algorithm for a binary search tree. So it's working in such a manner that it will compare the values of the root node. If it is lesser, it will traverse to the left side, and if it's greater, it will traverse to the right side, and thus the new node will be inserted in the appropriate position.
Binary search trees are trees that are specially organized for the purpose of searching. For inserting a new node, first the key is searched, and if it is not found in the tree, then it is inserted at the place where the search terminates. We start at the root node and move down the tree. While descending, when we encounter a node, we compare the key to be inserted with the key in that node and take the appropriate action. If the key to be inserted is equal to the key of the node, then there is nothing to be done, as duplicate keys are not allowed. If the key to be inserted is less than the key at the node, then we move to the left child. If the key to be inserted is greater than the key of the node, then we move to the right child. We insert a new key when we reach a null left or right child. First, we check if the root is null. If so, it stores the entered key as root. The insertion of a new node, the key to be inserted is compared with the root of the node. If key is found, then there's nothing to do, so we return. If the key to be inserted is less than the key in the root node, or if the key to be inserted is greater than the root node, we insert to the left subtree or right subtree respectively. The same process is followed till we reach a situation where we have to insert to an empty subtree. The two base conditions that we use to end the incursion is either when we find a key or when we reach a null subtree. The implementation of the binary search is showed using this program. The elements are inserted appropriately according to the position, according to the logic of a binary search tree.